Okay, so if you remember, we picked sprinklers with 8.5 liters per minute flow rate. And so our gross precipitation rate based on 55 um, meters squared area covered by each sprinkler, which was 9 by 6 meters. And this 8.5 is 0.51 meters cubed per hour, is 9.27 millimeters per hour. And then our net precipitation rate is 8.34 millimeters per hour. And so the reference ET we're designing for is 17 millimeters per day. And this almost never happens. But if we divide our 17 millimeters per day by 8.34 millimeters per hour for sprinkler, we have to irrigate for 2 hours a day. However we do that, we don't care. We're just designing the pipes. So the farmer can leave it on however long he wants on whatever days he wants, or she. Anyway, we're only going to irrigate for 8 hours a day because we don't want to irrigate the trees at night or in the middle of the day, preventing evaporation in the day and mildew at night. So we're going to have 4 zones because we're 8 hours of irrigation per day, 4 zones, 2 hours per day. Okay, and here's our property. So this is my design. I'm hoping you come up with a different design. You don't have to, but you should at least know how to do a different design if I ask you on the final. So really know how to do this one well if you just use this one. Anyway, what we decided to do was have 110-meter long laterals in the east-west direction. So we divided it into these 4 zones. And we have 110-meter long laterals going each way from the submain. And so we'll talk about that. And then we decided we better put the valve in the middle of the submain because if we put the valve here at this end, the pipe gets just way too big. In my mind, it's too expensive. So we're going to split the submain in half, just like we split the laterals in half, kind of. Split the submain in half. So that's a standard practice. And so we have 4 submains, but it's really a half submain each direction. And then we have a main line going back to the reservoir, wherever that is. And then just before the submain, we have a solenoid valve that opens automatically. And then we always have to have an air vent and pressure reducing valve. Relief valve, it's not a reducing valve. Whenever we have a place where the water could stop or blow air out and then stop, such as before a valve here, see how this is an endpoint? We don't have to worry about here because the water keeps going past here. But if this valve is closed and we turn the pump on real quickly, then we're going to have a stop in water flow potentially when it reaches this point, and that could blow the pipe hundreds of feet out of the ground. Seriously. That happened to our company once. I wasn't there, of course. I wouldn't let that happen. But it happens. It's like every irrigation company's favorite story, how they blew the pipe out of the ground this one time 10 years ago. Anyway, so we have a solenoid valve to control the flow. So we would have wires going back to the pump, or it might be by telemetry now in these days. And they would turn on the valve, or it would turn on the valve, and then that would allow the water to go to the submain and water the whole zone. So we'd say we had a typical day with 8 hours of irrigation. Actually, what we'd probably do is water this zone for 8 hours one day, then this zone for 8 hours, then this zone for 8 hours, this zone for 8 hours. And so we'd come back every 4 days to each zone. Or if we have enough water holding capacity in the soil, we might water this zone for 2 days for 16 hours, and then this one for 2 days for 16 hours and come back every 8 days, something like that. But anyway, we have a valve and we have an air vent to let the air get air out and the pressure relief valve here. And And then we have the submain or the main line going back to the pump. Okay, any questions? Great.
What about the reservoir?
We haven't designed the reservoir yet. The next thing we're going to do is design the centrifugal pump. On Wednesday, I'll talk about the reservoir and the groundwater pump. Okay, so here is our 110 meter long lateral with 18 sprinklers per lateral. 18 times 6 is 110. And as you can see, I've put in pipe between 1 inch, which is 25 millimeters, and looks like I made a mistake here and put 50, but 62 is actually 2.5 inch pipe. This is big pipe for a lateral. I don't really like that. It's going to cost me some money, but it's just what I had to do to have a lateral that long. You might want to have more more submains, so you don't have to have such long laterals.
Is the number given in like millimeters?
This number, 25?
Yeah.
Yeah, 25 millimeters is 1 inch. 50 millimeters is 2 inch. 62 millimeters is 2.5 inch pipe. And if you want to know the relationship, you look on the MM page in the spreadsheet, and it has the lists, I think, with both inches and millimeters. So what I had to do is I had to keep my friction really low because remember, I can only have 20% pressure variation in a zone, not just the lateral. So I had to keep my lateral pressure variation down around less than 10%, okay? So that I don't have to have too big of a submain. But maybe I could have a little bit smaller pipe here and have a bigger submain, but my total pressure variation had to be in the range of 20%. And actually, when I used to work for irrigation companies, we didn't even like 20%. That's the standard rule of thumb, but we would try to have much less pressure variation if we could. Although I was working in a hilly area, so we could always match the pressure loss due to friction with the elevation gain. So we would have almost uniform pressure. Okay, but this is a flat field. Anyway, if you remember for the 8.5 liters per minute sprinkler, the sprinkler coefficient was 0.827, and then the exponent was 0.5. And we have 0% slope going east-west. Our nominal pressure, that's 100, and that was to find the submain, the coefficient for the entire lateral. Okay? And that's where you press that button, calculate lateral coefficient. Okay. Anyway, we can see that each lateral carries 154 liters per minute, which is about 40 gallons or 35 gallons per minute. And so, but what we have here for the with respect to the submain is we need to consider both directions because laterals are going off our submain both directions. And so the spreadsheet is only calculating for one direction. So we're going to have to double that. So anyway, our lateral coefficient is 11.8 times x to the 0.499 or something. And for our submain, we're going to have to double 11.8. And so we have a lateral coefficient here of 23.6. So what this does is it allows you to calculate the flow in the submain as a function of inlet pressure. And inlet pressure to the laterals, actually. So anyway, that's why I entered 23.6 here and 0.499, and then that'll give you the submain flow for, now I have a distance of, go back up here, each of these submains Okay, so we've got 360 meters, and then so we have 90, 90, 90, 90. And there's 30 meters, 30 feet or 9 meters between submains. So we have 10 laterals for 9.1 meters between submains. We have 10 laterals on the submain. And so now with our submain, our lateral coefficient here, we can calculate our flows, and then we can put in our pipe sizes. And so you see my pipe sizes are going from 100 millimeters, which is 4-inch, up to 200 millimeters, which is 8-inch. So that's pretty big pipe. That's going to cost us some money. Okay. And I think what I did, I think I did calculate the submain coefficient. So it would be 97.14 times x to the 0.49. And notice for each submain, I have 2540 liters per minute. So now I can calculate my mainline flow at 50, 80 liters per minute. And so if I use Hazen-Williams equation, I get about 2 meters head loss. And if I use Darcy-Weisbach, I get the same thing. And I decided to use 12-inch pipe, which is 0.303 meters. That's the inside pipe diameter. And the reason I use 12-inch pipe is I had 2 meters head loss. And I really don't want to go up. I could use 14 or 15-inch pipe and have almost no head loss, or have like 1.6 or 1 meters head loss. I don't know what it would be. There's other spreadsheets in that pipe calculation spreadsheet that will let you evaluate the economics. So you could do that if you want. I didn't do the economics. But what you do is you compare the energy loss that you pay for in a pipe versus the capital cost of the pipe, and you reduce the energy loss back to present value for the life of your project. But I didn't do that. And you almost never do that in real life. You just say, oh, 2 meters sounds good. If you try to use smaller pipe, like 10-inch, then it's more expensive. It's more pressure loss. Okay. So then you have a mainline equation, which would, oh, I did calculate the submain coefficient here. It turned out to be 238. I just didn't show it on this one. So now I've got a flow versus pressure equation. Liters per minute equals 476 times the kPascals to the 0.5. But for my design of my main line, I'm just taking the 2540 for each submain, and then I'm multiplying times 2 for 5,000 liters per minute. And then I divided 5,000 liters per minute by 60 to get 84.7 liters per second. And everything else is pretty standard, like the C value, that's the roughness. I estimated my pipe was 500 meters long. I don't know if it really is. It depends on where you put the reservoir. So it would be, you always go from the worst case, which is this last submain in zone 1, all the way back to the beginning. And then you also, of course, you have this as a cost too, this pipe, but it doesn't figure into your worst. The thing about irrigation design is you're always designing for the worst case distance, worst case weather, and so on. Okay. So I designed my submain, 5,000 liters per minute. And now I need to figure out what my pump is going to see. So I'm just guessing I have 2 meters loss in the valve, 2 meters mainline pressure loss, which we calculated, and 2 meters of losses at the pump. I'm just guessing. So I have 2 meters of loss here in this valve. The 90 here is not going to be significant considering the main line is 500 meters long. 2 meters loss in the main line. And then I have losses around the pump. And I'm just going to say I have 2 meters of losses around the pump. That might be a little low, but actually in the chapter, it shows you how to calculate exactly what the losses are. So here's my equation. If I have 6 meters of loss, then my kPas, that's equal to 60 kPascals. So here would be an equation that expresses my flow. Kpascals at the pump minus 60 to the 0.5 times 476. Anyway, now I need to pick a pump. And so what we need to do is find a pump that pumps 5,000 liters per minute or 1,320 gallons per minute. I asked this to AI. And this was our favorite pump company back 40 years ago, Cornell Pump Company. Actually, now they say for ag, you should use Stay Right. But back when I was working, Cornell was the best pump for irrigation. And then Berkeley was also pretty good, not quite as good. So they're still around. Cornell Pump and Berkeley Pump and Stay Right Pump was there too. But they were mostly doing like well pumps. We didn't buy centrifugal pumps from them. But it sounds like now they're doing centrifugal pumps. But anyway, I asked AI to find me a Cornell pump at 5,000 liters per minute at 18 meters head. And why did I say 18 meters? Because, oh, and here's the lateral in the submain. I have about, I guess 0.5 meters head loss. So that's not bad. That's actually pretty good. So I went from 10.5 to 12.2. So that's less than 20% pressure loss. And so that would be less. That means your flow variation would be less than 10%. Okay, so I thought what we could do now is look up the pump catalog.
Wait, so why does it say 18 meters with that?
Because I have 12 meters head here.
Oh, that's the main line.
At the main line. And then I have 2 meters mainline pressure loss, 2 meters loss in the valve. I'm just guessing. 2 meters loss at the pump. I also might have a filter on there, so this could bump up to like 5 meters. That's something for you to think about on your design. I might want to say I want a 21 meter pressure pump at 1,320 gallons per minute, 5,000 liters per minute. Okay. That's why it's good. When we used to design systems, we used to say we're just going to add 5 psi for the pump fittings. For all the pump fittings, we'll just add 5. We didn't worry about calculating the exact amounts of each part of the fittings, valves, whatever. So that's the safety factor. And another fact is the pumps wear out. So having a 5 psi safety factor was a good idea anyway. And as my boss used to say, no farmer ever complained about a pump pumping too much water or having too much pressure. I mean, within reason. So, okay. So let's click there and we'll look at our pump catalog for our required conditions. Okay, so I signed into the Cornell Pump Company, which was my favorite pump. Actually, everybody's favorite pump 40 years ago. Not sure if they still are everybody's favorite pump. But I put in my flow rate, 1,320 gallons per minute. My total head is 60. I didn't know what static head meant exactly, so I put 59. This is a left or right angled pump. I said left. I didn't know what near miss meant, 90% of head. My next net positive suction head, that has to do with how high your pump is above the water. So I said it was 1, even though we're not planning on being above the water level. And I didn't know what margin ratio was either, so I said it was 1. And we picked clear liquid pump, 1800 revolutions per minute. I just did that based on, I think I remember that's the kind of pump we used to use. And these are just things related to electrical and others. Not sure. So then I said search. And here's all my options. And so what I want to do is I want to pick a pump in the sweet spot. And so you can see that this is the operating point that we've specified. And you can see the only one with the sweet spot right in there is this one. So we're going to pick that one. Hopefully.
What is that red arrow?
What is what?
What is that red arrow?
That's the operating point. And you can see, so what you do is you look for a pump with the operating point in the sweet spot. And the sweet spot, see, this is the highest efficiency, 84%. And then as we get farther away from the sweet spot, our efficiency goes down. And another thing we can see is that we're just ideally suited for this 9.5-inch impeller. So these black lines, these are the impeller sizes. These are the standard impeller sizes, okay? Which means this is the impeller they make at the factory, but you can ask them to change it. Like, let's say our operating point was right here. We could ask them if they could make us an 8.5-inch impeller right in between, and that would operate down here. But we want to, our operating point is right here. 84% is a very efficient pump. This, we might not expect more than 80, but 84% is great. So we're really, really happy with that. And we're really happy with 25 horsepower. Notice my operating point is right under the 25 horsepower, so I can use a 25 horsepower motor. You can never use a motor that's under your operating point. That's the way to burn up your motor. So you absolutely cannot pick a motor that is ever going to be above your curve, pump curve that you selected. So this is our pump curve with a 9.5-inch impeller. So again, these curves here, these pump curves are for certain impeller diameters. This is the 9.5-inch impeller diameter. These dashed lines are the horsepower lines. So you always have to be under the horsepower line. Let's say you had a pump curve that went above the horsepower line out here. Well, if you're sure the pump would never be operated at that point, basically with no pressure against it, then you could buy that motor. But if you think that sometimes you're going above that motor and you'll be up in here, if it ever operates there, it's going to burn up the motor. So you can never have your pump curve, a point where you think you'll actually be operating, be above the horsepower curve. That's almost the most important thing about this whole thing. The most important is we pick a pump at the optimal efficiency, which is here. And so we're there. I mean, 84.1, 84. We're almost at the peak. And the next most important thing is we're not operating our pump. Our pump curve doesn't go above our horsepower curve at a point where we think it's going to be operating. So anyway, we found our pump. This is great. And this even gives us a little bit extra if we need it, which is nice because we maybe should have added a few more feet of safety factor. So we found our pump. It's a 5YBH pump. This is what we used to do in catalogs. We would just thumb through the catalogs and look at pump curves. Now they find it for you. So they've eliminated the funnest part of irrigation design, unfortunately. Thumbing through the pump catalog. So I'm just going to copy this into my document. And so, like I said before, I had to sign in and become a user of Cornell Pump Company website. And if you don't want to do that, there's other pump curves on the internet that don't require signing in. But Cornell Pump Company is probably a very legitimate pump company since they've been around for 40 years, since I used to design irrigation systems. Okay. So this is our pump. And so this, you would just tell them, this is what I want. Or I guess you order it now. Request for quote. Yeah, maybe we should request a quote. But I think that they some salesman would have to look at it. Let's just yeah, see phone. So some salesman would call you. Let's not waste their time with a pump quote. And oh, and here's the NPSH. Okay. So that it's 10. And I've forgotten exactly the meaning of NPSH. I think this means you could be 10 feet above the water level. But you also have to consider things like losses inside the pump and the fittings coming up to the pump. So the book describes it clearly. It's just been a while since I've looked at that. But that's something you have to be very careful of, that your pump isn't like pulling water up farther than it can pull it up. Okay. And I didn't ask for a self-priming pump. So what you would have is a little primer pump on top of the pump to pull the water up into the pump. And then you would start it. And you always start it against a closed valve, and then you open the valve slowly. So, okay.
Why do you put the valves slow?
What you don't want to do is introduce water really fast into your pipeline, so it's flowing all the way down to the end with no back pressure, and then flowing up to the end, and then suddenly stopping, because that's when your pipe gets blown out of the ground. So you got to fill your pipe slowly.
All of the pipe search should be
Water hammer.
that, yeah.
Yeah, and there's programs in the Excel spreadsheet that do water hammer calculations, but we're not going into that for this project. Okay. Okay, one thing to know is, let's say we didn't have such a nice operating point and we were like above this 25 horsepower motor. You could buy the 30 horsepower motor and you're not going to be penalized energy-wise, because the 30 horsepower motor is only going to draw 26 horsepower if it's operating at a 26 horsepower spot. So you don't have to worry about your motor aligning perfectly with your pump curve. If you want to be safe with a 30 horsepower motor, you're not going to waste energy. Okay, so now we come to the reservoir design. And so in previous reports that we looked at, in basically phase one, I think several students, or at least one student, found that the well pumps supply 700 gallons per minute. And our orchard centrifugal pumps, for 5,000 liters per minute, they supply 1,280 gallons per minute. So if we run the well pump for 24 hours at 700 gallons per minute, this gives us 3,800 meters cubed per day, which is more than we need for the orchard, at least during normal irrigation, where we're just doing 8 hours a day. And then if we run the centrifugal pumps for 8 hours at 1280 gallons per minute, that's 2,326 meters cubed per day. So now you need to design your reservoir to handle the overflow and supply orchard pumps while they're pumping. So the well can't supply the orchard pumps while it's pumping. So you need to build up volume in the reservoir to handle the extra demand for the centrifugal pump during the day. So that's the next step, is for you to design your reservoir. You might have it be 2 meters deep or 3 meters deep. You need to have, I think, 5-to-1 side slopes, because cows or people could get in the reservoir and they need to be able to walk out. Chapter 20 talks more about reservoir design. There's certain like ends that maybe have less or more slope. But anyway, now you need to design your reservoir. And then on Wednesday, I'll talk about the specific design of the reservoir and where the pumps go on the reservoir, and how the maybe the pump pads and things like that. So anyway, I think that might be the last step in our design.